Okay, I think we can go ahead and get started. Professor, if you'd like to share your screen, and then I'm going to go ahead and give a welcome to everyone. Thank you for being here. Please note this meeting is being recorded, and so it will be up on our YouTube channel. My name is Julia. I'm the president of the Women Aerospace Organization at Purdue. While we have our presentation, while Professor's speaking, please keep yourself on mute and your video off so that we can focus on our keynote lecture. But she did request that as we have questions come up, feel free to unmute yourself and you can speak your questions out loud. Otherwise, if you have questions, please put them in the chat and we will get to them at the end of the talk. A little bit about the Amelia Earhart Summit. Women in Aerospace Graduate Women's Gatherings in the School of AE started the Amelia Earhart Summit in 2018. And this year, the purpose of the summit is to empower students by hosting events that focus on the diverse career paths and experiences from prominent members in the aerospace community. With that, I want to thank our lecturer, Dr. Seetha Raghavan, for being here today. Dr. Raghavan is a professor at the Department of Mechanical and Aerospace Engineering at the University of Central Florida, where she leads the Aerostructures laboratory. She completed her doctoral studies in Aeronautics and Astronautics at Purdue and her MS in Aerospace Engineering from ISAE-SUPAERO in Toulouse, France. She has 7 years of experience in the aerospace industry as a senior engineer involved in aircraft structural analysis, maintenance, repair and modifications, and non-destructive testing. She is an associate fellow of the American Institute of Aeronautics and Astronautics and was honored by the National Women Aerospace Organization with the 2019 Aerospace Educator Award. I would now like to welcome and hand it off to Dr. Raghavan. Thank you so much for being here.
All right, and it's great to meet everyone and to be part of this really great summit. I'm so glad to see it happen. We didn't have it in my time at Purdue, but when I first heard of it, it was just amazing that you have gathered together a lot of different people in all of these summits and made it very successful. So I'm really glad to hear about that. So a little bit about this talk. I wanted to kind of talk a little bit about industry and academia because I come from both. I spent some time in industry after graduating and then I kind of made my path towards academia, which is a little bit non-traditional. And I kind of broke it up into different timelines in that sense. I didn't do all of my education in one go. I had work experience and back to school and then work again and back to school, and chopping it up like that was a pretty unique experience. It was difficult, but it had its own benefits. So this is about my journey from industry to academia. And I am from the Mechanical and Aerospace Engineering Department at the University of Central Florida. We are located in Orlando, and we have a pretty large campus with about more than 70,000 students on the campus. And believe me, I didn't know this when I first came to UCF as well, that it is pretty much maybe the largest, I think, university in the country. So a little bit about me. At UCF, I'm a professor in the Department of Mechanical and Aerospace Engineering. I also I am a director of the Aerospace Engineering program within the department. Since I do research in materials and material science as well, I have a joint appointment with the Material Science and Engineering department. And we have a unique college called the College of Optics and Photonics here at UCF. And I have a joint appointment there as well, because a lot of my research focuses on using lasers for measurements and diagnostics. Since I work with materials, I also deal with nanomaterials. And so I'm affiliated with the Nanoscience Center. And I'll tell you a little bit about my research on advanced turbomachinery and propulsion as well. Materials directed towards engines. And that is why I'm also an affiliated faculty with the Center of Turbomachinery. I teach a number of courses. My favorite class that I teach is the analysis and design of aerospace structures. It is a senior level course that I teach here on structures and also on design of structures. I teach a bunch of graduate courses, some of which I started. So I teach aeroelasticity, continuum mechanics, finite elements, and I recently started a non-destructive evaluation of aerostructures here. And that's a really great class. I wish I had taken that class at Purdue. And I know Professor Grant taught that class really well. It just I didn't somehow manage to put it in my schedule, but I'm very familiar with the work he did, and it was just amazing. I did start up the aerospace PhD program here at UCF. We launched it in 2019. When I first came here to UCF, we had a program, a very large undergraduate program. We have more than 1,000 students at the undergraduate level. However, we had the graduate program only until the master's for aerospace engineering, following which most of the students who wanted to do the PhD ended up doing a PhD in mechanical engineering. There were a bunch of faculty who were working on research, which was very aero-focused. However, because we hadn't set up that PhD program, we kind of like worked in that process of doing the research in aero, but having the PhD in mechanical. And it was something that needed to be changed and needed to be expanded. So that was launched in 2019, and I'm really excited about that. It was something that I thought about as soon as I walked in to UCF 12 years ago. I worked in the industry for about 8 years. And like I said, it was pretty chopped up because I left, do my master's for a while, and then came back and then did my PhD after that. And it was a really good experience, but what I ended up finding was I really wanted to do a lot more research, and academia was the right space for me. But in my industry experience, I gained a lot of hands-on training and experience with the different aircraft types, mostly in maintenance and also in structural analysis and design. And this was really valuable to me. I also spent a little bit of time in France with a company, and this was part of the master's program that I was in. So I ended up being part of a validation testing for wheels and brakes of a helicopter. It was a pretty nice experience to be part of the validation tests. For research, I do research on mechanics of aerospace structures and materials. I focus on high temperature materials, thermal barrier coatings, and I'll tell you a little bit about that. Mostly my focus is on trying to get measurements that we never before tried to achieve when we look at materials. Typically, we tend to look at materials very microscopically and maybe in an ex situ manner. In other words, looking at them diagnostics after the fact. And here I'm trying to recreate environments that typical materials are exposed to, but be able to get really high resolution data while they are in these environments. And this is pretty challenging, but I'll explain a little bit more about that too. I'm also looking at developing new kinds of sensors with the materials that we have, and trying to create a means for us to diagnose structural health just using sensors that can kind of give us information about materials autonomously in the future. So that's just overview of what I'm kind of my hands in here and there. But where did I start? Well, I'm not going to go so far back, but I was really interested as when I was young in aerospace engineering. Mostly I started off being interested in engineering, and that's because my dad was an engineer. So I saw what he did. He was an electrical engineer working in a power plant, and I was pretty excited about all the stories he used to tell me about his work, and just learning a little bit about how systematic troubleshooting happens when you have your power outages and stuff like that. So I was pretty interested in being part of engineering and being hands-on with it. And he used to have all these little projects we used to do at home. Sometimes I would be helping him with it, and he always told me that I had a knack for it. So when someone gives you that kind of confidence, you tend to feel you've got some kind of skill in it. So I figured I would make a good engineer. Somewhere along the way, I started to find a passion for aerospace engineering, and mostly because I lived near an airport, and I used to go there just to watch the planes take off and land. So they had a really nice viewing gallery, and I would watch those the aircraft, and it's pretty interesting to me how something so large just managed to take off, right? And I wanted to know more about it as time went by. So when I went into engineering, my first degree was in mechanical engineering because I didn't have a place where I could get an aerospace engineering degree. But I told myself that the next chance I get, I would find a way to go somewhere where I could get that aerospace engineering degree. So it was already in my mind to do a higher level degree when I started my bachelor's. So when when I graduated, I wanted to do work in an aerospace engineering company. And I was pretty lucky because during my time as an undergraduate, I managed to get an internship with a company that basically did the maintenance and all of the analysis and structural analysis and upgrades for aircraft. And I was part of that internship that helped me to get my hands on analysis, and mostly analysis of systems in that company. And that experience kind of gave me a foot in the door and helped me to later on apply to a job in the same company. So I did get a job in the same company in a little bit of a different field. But the first thing I want to say is, as soon as I graduated as an undergrad and I became an engineer, I walked into work for the first week. And at the end of that week, I figured that I really needed to set some goals for myself, because, once you get a degree and you start working, the path in front of you is not really clear. You kind of say, well, what am I going to be doing for the rest of my life, right? Or rest of my career, at least. And you don't really have necessarily a fixed idea of what comes after what and when it should happen. So it felt a little bit uncontrolled at that point. And I was working so hard to get my bachelor's degree that I felt a little lost without that goal at the end. You reached your goal, you've been working like crazy to make that goal. Well, what's next, right? And I felt like there was nothing that told me, here's what the next challenge is. And so I sat down and I wrote a plan down, and I'm talking about like pen and paper. I made a 5-year plan. I made a 10-year plan. I knew I had some goals that I wanted to achieve, but they were all pretty, up in the air. There wasn't a timeline, and there wasn't a means for how I would achieve them. So putting it down on paper really helped me. I call it my infamous plan because my husband, who was not sitting next to me when I made that plan, had to kind of, in the end, go along with it. So it is an infamous plan. But that's the thing. You make a plan, and you then find out that your plan is not just you alone, right? There's everybody else with you that you have to think about. So a 5 and a 10-year plan was what I came up with. I don't know why, but maybe because I wanted to have something a little detailed and a little bit near term. And then I wanted to have something really far out there, long term. So that infamous plan kind of directed me and drove a number of things I did after I graduated. And I can talk a little bit about that. But first of all, my job. Well, I really enjoy my job. I can't talk too much about it, but I can tell you about what sparked the interest in research. So I started off with getting the job, and I suddenly realized that the job I had interviewed for was in maintenance, and I had interned in an analysis group. So it was a little different when I came into my first job, that I realized that I was in a group which is maintenance. When I accepted the position, I thought to myself that regardless of what I had experienced before, it's always good to have an open mind. And even if I did not know too much about what maintenance and what it was about and how I would grow from it or what I would learn from it, and if I was even going to be good at it, right? So I just felt like it was okay to put your feet in there and figure it out. I was right. I was pretty lucky that I was right. I definitely wasn't good at it to begin with. I came in not knowing a lot of things, and I found out the more I asked, the more I found out I didn't know. And with maintenance, it tends to be experience gets you further, and knowing your aircraft also gets you very far, because you kind of understand the kind of problems that you'd see in a particular aircraft type, and the design kind of drives some of the issues that you would find on it. And troubleshooting or understanding how to solve those issues may not be something you get out of a textbook. There are manuals that help you with some basic ideas on what to do, but then there are always issues that are going to be outside of the scope of a technical manual that tells you here's what to do when this goes wrong. Troubleshooting what it is that is wrong in itself is a problem. I mean, it's a skill you have to develop. So I'd say that I learned the most in this position that I was in, hands-on and in the shop floor, in the hangar with all of my of the technicians that I worked with. And knowing that your degree doesn't really give you everything you need in your first job is something that kind of what I saw right away. And that you kind of have to use that knowledge you gained, but in a way that helps you to learn more. And I learned a lot just being very open with the people I was working with, knowing for sure that there were various levels of experience, and I had to gain from that by letting them know what I didn't understand, and then just sort of soaking it up like a sponge. You just kind of get all that information, and slowly you start to build your knowledge on that area. So that was a really great experience. My day to day used to be, I'd be in my office on the 4th floor, and then would have a list of all the issues that we look at, and then I'd be up and down in hangars, to the hangars, up to my office, to the hangars, up to my office. I got a lot of exercise that way, walking across the entire place, and then talking to different people. So that was just the most amount of learning I did. It was in my first few years of work. But I had the opportunity to do a little bit of research. There was a research organization that was interested in working with us to do the detection of fatigue cracks on the underwing skin. So on the skin of an aircraft, you have the upper wing and the lower wing, and typically in flight, you have tension on the underside of the wing and compression on the lower side. And as you land, of course, then it releases the stress. So that load sort of cycle of tension and then release of tension, and again and back and forth. It is a cyclic load that is created by flight, and which leads to typically fatigue cracking on most aircraft. So aircraft wings in general have fatigue damage, and to resolve this damage, first of all, you need to be able to detect it and then figure out a way to solve that problem. So the design of an aircraft itself, or the wings, are already in place to adapt to this issue. So typically you'll find the kinds of materials that are used on the underwing skin are going to be fatigue resistant to a high degree. And the methods used to install the aircraft or have designs are used to alleviate the issues of fatigue. But of course, there's not much of a way, at least in the past, to reduce the number of stress concentrators, which are the rivet holes that hold parts of the spars to the wing. And these rivet holes end up being sources of fatigue crack initiation. And we want to be able to reduce this, but at the same time, we want to be able to detect any damage, right? So the detection of damage was where the research project ended up being focused on. We looked at trying to find a way to identify where damage happened around these rivet holes. And if you think about the rivet holes, there are going to be numerous, thousands of them, and under a wing skin, and the inspectors have to pretty much use different kinds of techniques like ultrasonics or eddy currents, and kind of inspect each of these holes. So you'd imagine there's a vast amount of time that's spent doing that, but a vast amount of skill is also needed to achieve this, because looking at the signals around, these rivet holes requires you to be able to look at the signals and then detect if something is not right about it. So how do you kind of automate that process became a research project in a way. And that's kind of the focus that we had as we were working with a research organization to do that. So it was a very interesting topic. And, we came up with a robotic system together with the research organization. We came up with a system and a method of calibration, a method of detection, step-by-step processes and analysis codes, and everything that kind of, when put together, ended up doing robotic inspection of underwings of aircraft. And this was a really interesting project that ended up giving us a patent. So it was part of the research that enabled that patent to be filed. And that whole experience gave me the idea of how research was kind of at the forefront of technology, and I really wanted to be there. I wanted to think about something that was 20 years into the future, design new things, and perhaps have my own ideas come about as something that I could see kind of turn into real systems in front of me, right? How would I do that? And the first place I thought of was being an academic, having my own laboratory and being capable of writing up my own research ideas to get grants and come up with these things. So that was kind of like what I wanted to see as part of my future, right? Freedom to do research and also take some of the credit for it. So I'd say flexibility is important. Now, the first step to that was, well, I needed to get my master's. That was already in my plan. As an undergraduate, always wanted to go all the way. And maybe when I was an undergraduate and I thought about going all the way, like getting my master's and my PhD, my goal was, well, I really am passionate about aerospace engineering. I want to get a higher degree, specifically in aerospace engineering. I knew I was going to do my master's. But why not go all the way and do my PhD? Just because, it's possible to do that if you really put your time into it. And because why not go all the way and learn all you can or get all the skills you need in a field that you really are passionate about? So the master's was the first step. I found a fellowship that offered me the ability to go off to do a master's in aerospace engineering. And this was in SUPAERO, which is a very well-known French university in the south of France, in Toulouse. And in fact, that is kind of like the capital of the aerospace capital of France, right? Where everything happens. Airbus does its integration of aircraft over there, and CNES, which is the space agency, has its facility out there. And so it's a really great place to do your degree to learn about what goes on. And it was my first experience being away from home and learning about meeting people from different places who were interested and passionate about aerospace engineering, just like me. And it was a great experience. So we started off with 3 months of just learning French. And again, the master's was going to be conducted in French. So I did not have any background in French at that point in time. So I was kind of signing up to do a master's in a language that I did not know. And it was, I guess at the time, a little bit difficult, I would have imagined, but somehow it didn't faze me. And I'm the kind of person who hops onto the roller coaster and then freaks out when it starts. So I guess that was what it was. I figured, well, if someone else did it, I surely must be able to. And that's what I was told. There were people who didn't even have the same, I write in English. So it's not like I have to learn another script in another language. I just have to learn the language. And so it can be that bad, right? Well, I'm lucky that I think I have a little bit of a knack for languages. So it did work out that after 3 months, I was really speaking in French. And the trickier part was trying to learn engineering in French. That was harder. So getting around town, talking to people, and I was pretty lucky that maybe in that period of time in the 90s, when you were in the south of France, you really had to speak in French to survive. So it wasn't very cosmopolitan. And so people spoke only in French. And if you wanted to get anywhere, you wanted to take the bus, you wanted to buy stamps, you wanted to make a phone call in a payphone, which is what we used to do at the time, then you just have to speak French. And that was great. That was great for me because I learned really fast. So 3 months was all I needed. That immersion did it. And I think I would not have had that fast of a progress if I had tried to learn it on my own, back home anyway. What was also great was I met people from so many different countries because we were all together trying to learn French to be prepared to start the master's program. I met people from Switzerland, from Italy, from everywhere, basically. We all had a common goal. We all were interested in aerospace engineering in different aspects of it. And just being part of that group was really interesting. I got to see a lot of nice, locations around France as well. Not too much, not too far, but around Toulouse, they have the Pyrenees, which is the mountains that separate France and Spain, and they're really beautiful hiking spots out there. So I spent weekends just doing that, and it was great. I lived right next to the Canal du Midi, so you can see that in that picture over there. It's a really nice canal, and I wanted to point it out because it is an engineering feat in itself. The way that it was designed, to raise the levels of water and reduce it when needed so that all the boats could pass through. So that was pretty interesting, and it was a very exciting time for me. The south of France and Toulouse in specific it was exciting at the time. They were talking about the missions to Mars for the rovers, and they were also talking about, and there were also a lot of different aircraft that they were putting together at the time. It was most interesting to see the Beluga, which is the aircraft that really looks like a whale, I guess. So, and that was a design that just learning about it made me pretty excited because it was a modification of an actual aircraft that was previously designed, and how they had done that modification is a real engineering feat. So learning about some of these things and then visiting some of these facilities was very exciting. But of course, the classes were not easy. So it was a fellowship. I wanted to do really well, and I was trying really hard, but I had trouble in class. There were class times when I sat there and listened and furiously wrote all my notes, but I could not absorb the information and translate it in my head as fast as it was coming to me. So I could never ask the questions in time. I could never ask the questions in the class because I didn't really understand what was going on. I was just trying to gather the information, go back to my dorm and then read through that. And then I'd have a bunch of questions and I'd have to go back to talk to my professor to figure out what it is I didn't understand and get some answers. So it was definitely way harder than it would have been if I was doing this in English. And but I really appreciated that I had that experience because I would never take anyone who sits in a class and doesn't speak in English or have a native English speaking capability. I just have so much respect for them because I know that it takes 2 times the amount of effort to get the work done because you have to put in the extra time to learn what you don't understand and to get proficient in writing answers in an exam is harder. Everything gets harder, and I think that it just helped me to learn a lot more, to appreciate it, and to help more students. And so when I walk into a class and I know that it is not native language for a lot of students, I know what I need to do in order to support them and to help them to adapt to the and work with their pace, because it is definitely a lot of work. So just as an example, I took a class in flight mechanics, mécanique du vol. And in that class, it so happened the professor decided that he wanted to do oral exams. Now that's like my worst nightmare. Not only did I have to think, understand his questions, I'd have to formulate my answers on the spot in front of him. And he was kind of scary, to be honest. So it was hard, and I had to find ways to deal with it. So this is what I did. I sat there and I thought, okay, this is going to be a disaster, because I can figure out my answers, but I'm not going to be able to answer it well if I don't prepare ahead. But how do you prepare, right, for an oral exam? So the way I did it was I had to think of all the different questions he could possibly ask. And of course, there would be some overlap. Maybe he would change it a bit, but every possible question I could think of, I think I came up with 25 different things that could possibly be asked. And I wrote out answers to each one of them in French. And then I sat there and went through a whole preparation of how I would answer it. And so I had to do that kind of stuff for this class. And it was difficult. So I guess what I'm saying is that one way to deal with a challenging situation, we always end up with them, is to find your means of trying to, no matter how crazy that method is, even if you had to stand there and practice your answers, do whatever it takes for you to be confident when it comes to you having to face the difficult situation. And nothing is impossible if you kind of put your mind to it. I was pretty lucky that, some of the questions, and I knew that would happen, that, there would be bits and pieces of questions that I thought about that ended up being, things that I could explain as part of my question, the question that was asked to me. So it's really possible to deal with really difficult situations as long as you kind of put your whole heart in it and find a way, right? But I did tell myself, and I wrote this down, because I am, like I said, the person who gets onto the roller coaster before it takes, and then freaks out when it starts, right? So I told myself, well, don't write it down, because you're going to forget how hard this was. Write it down that when you do your PhD, you're going to do it in English. And I would have been happy to do it in French as well, but I really wanted to focus on learning the content and give it my all. And I knew I could do that better in English. So I guess one other thing I would say is that, truly the point of the matter of, if they can do it, then you can. It really helps sometimes. So whenever someone gives you an opportunity and you're thinking to yourself, am I going to be able to do it? It always helps to kind of say, well, if someone else did it, then I can too, right? So there's my class, and you can see that I am the only girl in that picture, but there was another. I think she just didn't turn up that day, and I guess not much has changed. I hope it does change a lot more in the future. But that's the next step. I went back to work for a couple of years after that. I moved from maintenance to analysis and design, which I really wanted to do analysis. But somehow maybe being in the hangars all the time, being with the aircraft all the time, being in an analysis situation where I'm just stuck behind a computer wasn't as exciting as I thought it would be. After some time, I decided I'm going to go off and do my PhD. It was hard by that point in time because I was so entrenched in my work. I was so full inside of my work. I had so many different responsibilities at work that just stepping away from it was harder than it would have been if I had just gone through and done it continuously. But of course, the experience gained in a work environment is something that I didn't want to miss, and I'm glad I didn't. Well, the infamous plan was that I needed to get my PhD done. That was in the 10-year plan. And I had actually set myself up for it because I took the GRE right after I graduated, when I finished my undergraduate. I took it when I did not even have a plan to do graduate school. I just took that GRE, and in my mind, I told myself, you got to take it so that it's one thing off your list. It won't be another excuse to say, well, it's hard to do a graduate school because I have to go take my GRE. This is another hurdle. So take it when you're fresh, right out of your undergrad, and get it done, right? And that's what I did. And at that point in time, it was 5 years past that GRE, and it was about to expire. So it was this: if I wanted to apply for a PhD, I would have to end up taking my GRE again if I did not apply right then. And it's a crazy thing, but that is what kind of gave me that push to apply. Now you're going to look at this and see, well, there's a bunch of application letters. There's a bunch of acceptance letters. There's an acceptance in 2001. There's an acceptance in 2000. I basically got accepted to Purdue, and that was the only university I applied to, by the way. That then I had to put it off again and again and again because I hadn't set it up right. It wasn't easy for me to go. I had 2 kids. And I had to think not just of myself, but of them, and how I would manage all the logistics of this goal, or this quest to do the PhD became a lot harder than I imagined. So I was pretty lucky that, look at Purdue, they were just amazing. They deferred my acceptance to grad school again and again and again. In fact, when I did arrive, they said, hey, you actually finally made it here. And that was really great. That they did that for me, because it was so important that someone was patient on the other side waiting for me to turn up. I did get to work with a professor at Purdue. His name is Dr. P.K. Embry, and he used to teach the Intro to Engineering course. And at Purdue, I was working on the aerospace and in the aerospace Aeronautics and Astronautics, doing research on materials and structures. We were looking at different coatings and high temperature coatings and how they performed under different conditions, but creating a model for sensing the stresses in these particular materials that are used in these coatings. So there's me with Dr. Embry. He's at the beamline with me. We're doing experiments at the Argonne National Lab that's not too far away from Purdue. And I did a lot of different things at Purdue. So I didn't just do my research. I was also a surf mentor. So that's my surf student, Jared, right there doing his experiments. And I met him recently. He's working at NAVAIR, which is just amazing to meet people, after so many years and see how they've grown. So I also have great friends out at Purdue. I would say that staff at Purdue are just amazing, and they kind of helped me through, right, with all the difficulties or whatever I had. I will always be able to count on them to kind of help me through that. I also took the opportunity to get involved in a lot of different different things that are available to students, so grad students out there. For example, there's a future faculty fellowship that was run by Dr. Rebecca Richards Gordon out at University of Texas in Austin. And she ran it for, all graduate students at that time in different universities who were interested in a faculty position. It was focused on women in engineering, and I applied to it, and I managed to get to be part of it, where they taught us how to put together a research plan if you wanted to apply for a position as an academic, how to put together a teaching plan, and how to make a presentation at your interview, and all of those things, how to ask for what you need for your laboratory. So there's so many aspects to being a professor that you wouldn't know about unless you kind of met with people who are, or you're part of some kind of future faculty workshop. There's a lot of different ones that are being offered. So if anyone is interested, you should try to go and use these opportunities to help you, kind of elevate your position in getting an academic, a step in the academic field. So that was great. But, my time at Purdue was not just about me. It was also about my kids. So we lived out in Purdue Village, which I understand is no longer there. We spent time, they grew up there. There was Spring Fest, there was a school, and there was bowling at PMU. There was all kinds of stuff. And there was soccer, there was, classes for art, there was all kinds of stuff. So I wasn't just doing my research, I was also doing all of this other stuff on the side. And at this point, when I think about it, I can't even imagine how that happened, how I managed to do all of that. I remember I put my kids to bed at 8:30 or 9, and then I head back to the lab and I get my research done all the way until like 2. And then I come back home and sleep and wake up and send them to school. And then I go to all my classes, go pick them up from school, bring them to whatever they needed to. And it was just pretty hectic, but it got done. I had a lot of help from family. My mom came to help me sometimes. My husband came to visit. He had his job back home. So it was pretty hard. And, I am from Singapore, so that's where he lived. And so it wasn't easy for people to come visit me because it was really far away. But it got done and everybody looks happy right there. So it was okay. Now my kids are in college, and when I asked them about their time at Purdue, I think they kind of saw how much I had to work. So they understand what grad school is about. It's a lot of work. They were doing homework, but I was doing homework with them. And so we were all kind of working together for the different things, right? And it was a lot of fun as well. I want to talk a little bit about research at Argonne National Laboratory. It was a great time for me when I did that because I was looking for a place to do my research, and Argonne was a great place to do it. It is just 2 hours, it was just about 1.5 hours away from Purdue, and it has a lot of different facilities. I had gone there to do a summer school, and that's another opportunity I took. And it helped me to apply for beam time, to do some really cool experiments out there. And I managed to get time and learn the hard way that research at Argonne or experiments at Argonne happen 24 hours a day if you want to. And of course, I wanted to use every minute that I could get. So I had a 5-day experiment experience out at Argonne, which really made me learn about how to organize my time, how to run the experiments well, and use equipment I had never used before in such a short period of time. Well, at that point, I became a professor. That was not easy to get a job as a professor. I applied to many different places, but eventually I did get one, and that was out at UCF, and I'm really glad I'm there. There are so many things a professor does. Strategic areas, you have to come up with new ideas. You collaborate with different people, you get funding, you write proposals, you have to figure out what equipment you need. You travel to meet different people, you present, publish, you go to conferences, you teach classes, you mentor students, you meet people from funding agencies, publicize your research, and then you, within the university, help to serve to improve the teaching, the research, and all the different aspects. Student support, developing students, mentoring. There's so many different aspects, and that's kind of what I like about it. That you're not just doing one thing; you're doing so many different things. But here are the cool things about being a professor. If anyone has that in their mind. I know I never thought about it when I was an undergrad. I just knew I wanted to do a PhD. I didn't know what I wanted to do with it, but the more and more I thought about academia, I just was more interested in being part of that, to have my own lab. So you come up with an idea and you see it come to life. And that's, something that I couldn't think of getting anywhere else. Reinventing myself. Sometimes I take off for a year, get an opportunity to go work somewhere else, and that's part of a sabbatical. So I spent some time at the University of Sydney And that was really exciting. We developed new areas of research just based on that. You set your own pace. You work fast or you work slow, whatever it is, you want to do. You get hands-on when you want. And so sometimes I'm out there in the lab doing my research with my students, and then until they kick me out of the lab, or sometimes I'm writing or planning, you get to make a difference. And I think that's the biggest part. How much of an impact you have, I think, is great. When you're a professor, you get a chance to create new fields, create new courses, and create new research ideas. And you have your summer to really, explore your own goals. You can create your own goals and explore them. And there's energy all around you because of students. But here's my research theme that I worked on in academia. As a professor, I need to have a research theme. And my focus was on extreme environments and aerospace environments. So looking at high temperature coatings, materials, and looking at engines and how to develop higher, more durable coatings materials that can take the environments that we subject these engines or aircraft to. So we know that the future is about having more powerful engines, faster flight, right? And a lot of times this can't happen without designing structures and materials where you have improved strength and durability to high temperatures, but at the same time, strength to weight ratio needs to be acceptable as well. Extended life, and with high speed vehicles, you're trying to deal with aerothermal effects, but reusability is important. So it's not just about surviving one flight, it's about being reusable over multiple flights, which are really extreme. So how do you deal with that? Sometimes you have the need for multifunctionality. And so that's an aspect that needs to be taken care of as well. And my approach in the lab was kind of threefold. We're talking about trying to capture response of materials under extreme environments to understand how they fail and what are the mechanisms that they fail, what are the mechanisms that cause them to fail. And I think with that kind of understanding, you have a better chance of designing new materials that can take it. And some of that design has to be really unique in the sense that you'd have to tailor materials either through the microstructure or the mechanics and find a way to develop more resilient materials, either trying to functionally grade them, add material additives, dopants to materials that elevate their properties, or treat or process them differently, or improve manufacturing technology that helps you to maybe reduce some of the effects of the external heat that comes from, say, high-speed flight. I'm also very interested in developing new kinds of sensing technology, especially to use multidisciplinary approaches like optics and fluids or aerodynamics in conjunction with materials to be able to elevate material properties. So sometimes it's not just about one field that can resolve the problem, but a combination of fields. And I think that, being multidisciplinary is probably the key to more novel technologies in the future. So that's kind of what the lab focus was about, and a lot of mechanics is involved in this. So here's the focus on the engine environments. So we were typically looking at these coatings, which are very thin. They're maybe like 200 microns thin. And what they do is they protect the turbine blades from extreme temperatures. They're thin, durable coatings, and they're ceramics. So, ceramics are kind of brittle, but the microstructure here is what resolves that issue to some extent by depositing these ceramics, even though they're really thin, in a way such that they have these porosities inbuilt. And that porosity, if you look at this finger-like or needle-like structure, helps you to have that kind of compliance that typical ceramics don't. Typical ceramics in bulk form are very hard and very brittle. But having that compliance built in the microstructure helps them to take different kinds of stresses without, failing catastrophically, which is what ceramics are known for. They're very quick to fail when they get impacted, or they have issues or large drops in temperature. I did go back to A&L. So this was one thing that I thought was really good. I wanted to go back there to do more research. And so you see that, that one experience with summer school down there turned into multiple trips to A&L since I've come to UCF. And I've brought a lot of people along with me. So this is kind of what I mean by maybe sharing experiences, giving back, and going full circle. So in a way, that one summer school where where there's a group of people who invested in my time to be taught how this, argon works and what the National Lab does is a positive impact if I take that knowledge I gained and spread it around and bring more people on it. And so number of my students have got their thesis work done, their dissertation work done out at A&L. And it's been really positive. And I just wanted to show you.
One of the most memorable things about argon was the learning curve. I've never been in a spot that I've had to learn that much in a short period of time, but also given the opportunity to take the helm and do all this engaging research as an undergrad. And this was something that was very empowering and very motivating to want to pursue more advanced research.
So that's Renee, and he tells it like it is. We have a lot of it's a huge learning curve, but the experience is something like you can't get anywhere else. So I started to do all of my high temperature coating research over there. We expanded a lot of the works to enhance durability of these high temperature coatings, being able to capture the material's response, and having our first data come out on tracking strains under temperatures in the order of 2,500 Fahrenheit, implementing thermal gradients and understanding how internal cooling in turbine blades and external heating affects the strains in these really thin coatings, giving us the idea of how to reduce the effects of these extreme environments on them. And I have partnerships with the German Aerospace Center, which is something I wanted to say as well. The scientific collaboration is really critical, and reaching out to find the right collaborators are really important. So I had reached out to Dr. Marion Barsch, who is in DLR in Germany, and also Dr. Annette Carlson, who is now the head of president of the University Embry-Riddle in Arizona, Prescott. And at that time, she was doing a lot of research on computational studies for these high temperature coatings. And Dr. Barsch was out in Germany doing a lot of research on thermal gradient mechanical fatigue testing of these coatings as well. So I had a lot of experience with synchrotrons, and I wanted to bring us all together to do all of what we're doing concurrently. So here's what the setup was. It wasn't as easy as we thought. We were trying to recreate the extreme engine environment with thermal gradients in a synchrotron. So we had to design this new setup where we could sort of, create an environment which was typical of an operating environment in a turbine blade or turbine section of the engine, but still be able to capture the data from these really thin coatings with extreme resolution. And synchrotrons help with that because there's very high energy X-rays, and energy is related to the wavelength. So basically inversely, so you can really go down to atomic scale strain resolution if you are using that for measuring, you're using the diffraction to measure strain. And I wanted to just talk about scientific collaboration, so I'll let you listen to this.
We were working at the German Aerospace Center with Dr. Marion Barsch and a team of other engineers there. to help develop our system for implementation at the synchrotron. DLR has a long experience working with TGMF, or thermal gradient and mechanical fatigue setups, one of the only places in the world where you can find such a system that's used to rapidly test and characterize different turbine samples. While we were there, we were working directly with both Janine and Carla and Dr. Barch. We were able to learn a lot from the previous decade of research that DLR has done in developing their system, learn what does work, what doesn't work, and what was the most effective way to collect measurements. And then we took our expertise with the synchrotron and taking X-ray diffraction measurements, and we were able to blend the two together to be able to form an apparatus that proved functional and provided great results in just less than 6 months. We worked with a number of great scientists and researchers while we were in Germany. Specifically at the DLR facility in Cologne, we worked with Dr. Scholz, who is one of the experts in coating technology, and it was incredible to see the machinery that's available and the process he goes through to make our samples ultimately.
So since then, we've sent more than like 20 over students as part of International Research Experiences program that NSF has funded, the National Science Foundation. Just bringing all of these students out to DLR, the German Aerospace Center, and then working with the German scientists when they come over to the US to do the experiments has been really valuable just for student development and all of that. But I just wanted to point out that this whole conception of this idea was a part of my goals and passion for international education. And I think that, research abroad and study abroad is it really opens your mind. So having that experience is really critical to, or important to develop you in ways that you can't typically be developed in just being in one place. And I know that as a student who was exposed to that. So finding a way to put that into my portfolio of what I wanted to do was important to me, but that freedom to do that is what my position as a professor allows me to, to be able to conceive these ideas and to bring everyone with me on it. I also like working with industry. And so industry is one place that I want my students to have as much time at. So I have been working with Boeing, and I have my students go out there to do experiments. We come up with methods of damage and stress sensing coatings, or creating them. Projects that are research-based but need to be applied in an industrial environment is really what I want to focus on a lot of times. And so I get the chance to do that as well. So this is one of the projects we worked on, where we look at nanoparticles and put them into sensors and coating as sensors in a coating, and have them kind of tell us how the structure underneath is behaving, being able to capture damage when it starts to happen at an early stage can be helped by these nanoparticle sensors. Probably the most important thing that I felt like was a contribution that I never thought was going to be the most important thing was the PhD program at UCF. I came into UCF saying, well, I want there to be a PhD program in aerospace engineering. I don't think I want our students to have to do the PhD in mechanical. We have to set that path and make it possible. It wasn't something I could start doing as a new professor, but once I came to a point where I was in my position that I could put the effort into making that happen, I made all the effort, directed all my effort towards it. And it was so much more about what I felt like I would want as a student that drove me to do that. And it was never something that I thought was going to be so impactful until it happened. Because the first year we had 34 students who came in either transferring from their mechanical program or applied to, and the second year we had a large amount of applications. And it just seeing them, come to this program, which wouldn't have been there if I hadn't wanted it as much as I wanted it, then I think that impact is something that you can't really feel anywhere else. I mean, whatever paper you wrote or publication you produced is not going to give you that much of satisfaction in terms of having an impact. So I think I really made myself useful there in wanting to make this happen. And when I did it, I didn't even think about what it would, how important it was. But every time someone graduates from that program, it's like a gift to me. Like I'm glad I'm glad I didn't give up, and I'm glad I really pushed for it. And I wish I had known how impactful it was. I would have pushed it much faster, And I think that sometimes your best contributions come from a place where you don't really have an expectation. You're just kind of thinking, well, I wouldn't do this PhD if it wasn't in aerospace, and I don't want any of my students to do that. So just watching them succeed is just amazing. I have collaborators within UCF that I work with, and Nicole Galford, she's no longer there, but I figured a little bit about mentoring that I never thought about. So discovering mentoring, and I just do it naturally. I don't think about it as something I have to do or part of my job, but I learned a lot from different people on how to mentor students. I don't think I am perfect in it. I have a lot of flaws when it comes to managing my students, and I try to learn from it every year. To get better, because every student is really different, and it's really hard to find one way to get through to them or inject excitement in their work or help them to get through their challenges. Everybody is different. But I do know that before I point out a negative in a person, I always have to think of their positives. And I learned this from someone at Purdue: to inspire and expect nothing in return, and to have some kind of passion for mentorship. And Nicole was like my partner in trying to help students get fellowships. So I'm really always looking for people to work with like that. Role models are also important. At the bottom there, you see my professor, Dr. Embry, next to me, and you see his professor next to him. So, it's kind of like we're all helping each other out. And I think that, one of the ways is to always ask people how they overcame certain challenges that you might be having. What can they tell you that may help, and what do they have, and how can they help you? So people out in Germany helped me. I didn't even know them. I picked up the phone, called them up, and they actually helped me. And we have such a good relationship right now. And so many students have benefited from it. So it doesn't hurt to reach out and get help, and especially to have role models to help you get through. I wanted to point this one out just as we get to the end of this long talk, I guess. I've always, and this is future looking. So now I'm thinking about the future and what I want to accomplish. My 10-year plan and 5-year plan have long since passed. So I asked myself, do I want to write another one? And I was told, don't do that, because you get so driven just because you have these things you need to accomplish. And how about just not doing that for a while, right? But in the back of my mind, I can't help but have one, and I know that I want to write a book. Why? Because, and it's a textbook. It doesn't sound very exciting, but it is for me, because as an undergrad, when I was an undergraduate student, I really appreciated the 2 books that really gave me passion for aerospace engineering. I was very interested in aerodynamics. So I'd read John Anderson's book, and I'm sure all of you have. I had been working with that in my class, and all of his books actually. And then I used the analysis and design of flight vehicle structures from Elmer Brun, and Dr. Elmer Brun is from Purdue. And you'll realize I said I only applied to Purdue when I wanted to do graduate school, and it was because of this book. This book was useful for me in my classes, but even outside of it, as I went into work, I used this book for all of my analysis, for my design, my analysis work in a work environment. And someone who can write a book that's useful for school and still be useful for work is pretty impressive to me. And just being in doing my graduate school in an institution where that person was a professor was what I looked for when I decided to apply to graduate school. And it's pretty crazy. So I told Dr. Anderson when I met him that when I was an undergraduate, I told myself I'm going to do graduate school. And if I was going to do graduate school, I'm going to do it in one of two places. I'm either going to Purdue or I'm going to the University of Maryland because these two books are just amazing. And he said, well, where did you go in the end? And I said, well, I did all of my work experience in structures. And so I decided to go to Purdue. But, you know, I have a passion for aerodynamics. So I always have that at the back of my mind as well, that I want to kind of expand my research. And of course, we do a little bit of work on aeroelasticity, which combines the two, but to do a little bit more sometimes. And then I asked him, well, you know, I really want to write a book that would inspire students the way yours did, you know, that it brought me all across just to come to Purdue just because of this book. So I want to write a book like you did and like Elmer Brun did. And how do you find the time to do it, right? Because you have research, you have your classes, you have teaching, and how do you actually find the time to do this? And he told me that, you know, take a day in the week, just one day, and drop everything and get started. And if you did that, it's kind of like a place you escape to. Every week you have this one day, and you'll find that you're going to look forward to that one day where you drop everything and you just do that. I haven't got the ability to start doing that, but it's in my mind, and one day it's going to happen. So in the future, here are my directions. As usual, I'm planning in the first 1 to 2 years and the 5 to 10 years. I can't get that out of me, but I do want to build on my research topics, expand. I work with some projects from DARPA and also with industry. I want to work more with different industry, companies in industry. And I want to expand on my research and international collaboration. I want to increase my collaboration, not just to 1 or 2 countries, but maybe to more, create more opportunities for people to come here and for students to go out to different places to do research. Like I said, the value of it is just can't be explained. I of course want to expand the aerospace graduate program that I kind of so invested in. Increasing visibility and helping students to succeed in the program. And in the long term, I really want to go further than that. And especially, you know, it has been hard for me to really build a platform to help women in engineering, but that's something that I have been always passionate about wanting to develop. And so I feel like I may be able to do more at this point and hope to do that as well. All right, so I guess I went beyond the time I imagined I would, but if there are any questions.
Thank you so much, Dr. Raghavan. Yeah, and if anyone has any questions, please ask them in the chat. It looks like you have one now.
Oh, right, so. As a new prof, how do you go about coming up with new research ideas when you've spent so long as a PhD focusing on? Yes, that's really true. And where do you get the energy to? Okay. So the first thing is new research ideas. Where do they come from? Well, in a way, when you're doing your PhD, you're very focused, but you start branching into various different areas to get your research done, right? So I used to think that you'd only be good at really one thing by the end of the PhD, but I found out that, you know, to get that one thing done, you have to pull on different areas. So I started to get more knowledgeable about things in optics. I started to get more knowledgeable about X-ray diffraction and what it does, and just being exposed to so many different disciplines just to get my one problem solved ended up giving me a lot of different ideas from those different disciplines. And I think it's also helpful that you're going to have these ideas while you're doing your PhD and say, oh, this person's doing this research that's really interesting, and how do I weave that into what I'm doing, you know? And those are the kind of things that ended up being research ideas that I started to put out there. You know, I started to just read a lot from different disciplines, and that helped me. energy, I wish I had more energy. Now, as a grad student, like I said, I hardly got any sleep. I don't recommend that. I wish I could have done everything without sacrificing my sleep and and that I think is the worst thing, right? Now I mean, I definitely have toned down a lot as much as I can, and I think maybe when you're younger you have that energy, and as you get older it becomes a little harder to do that. But I get my energy from my students, I'm gonna say that now, because they are so excited about moving forward in their research. I can see that. So sometimes when I'm thinking like, oh, I want to kind of relax this summer and not have to focus too much on 5 different things, I'll just focus on 2 instead. And then I find out that, my student says, well, I'm have these plans to get all these things done, and so I have to be there for them, and I have to be on top of it for them. So I get my energy from them. They kind of give me that push. What has been the most memorable and enjoyable project that you've worked on? I think my collaboration with the researchers out in Germany, that has been the most exciting, because we managed to achieve something that no one else has achieved. And I think I'm always about that. I want to be like, oh, the first person who got this done. So when I first came up and said, well, I want to see what goes on inside the materials, inside the engine, and I want to have that in the extreme resolution that we can. And someone was like, how hard, that is really hard. Why would you do that? Just, expose these materials and look at them after. And I was like, no, we're going to miss something. The in situ is absolutely, and made that happen. And just having that happen, like to do something that hasn't been done and just blowing everybody's mind, like we got this done, right? I think that, coupled with the fact that it was an international collaboration, and coupled with that was that these were 3 women professors who got together and made something happen. All of that just made it really exciting. The next question I see is, how can someone who is about to graduate help ease the transition to full-time work? I think, actually, I think when you say that, I'm guessing you mean like with when you're a student versus when you're full-time working. I almost feel like working is a little easier in terms of time management, just as if I'm talking about like being a professor and being in industry. When you go to work, and if you're in a company, you have a fixed time. You typically don't come back and end up doing your work as well. I find that the problem with when you're in grad school is that you're thinking about your work all the time. You don't, you leave your lab and you go back and you're going to be doing it some more. Just, you have to like find a way to stop yourself, and it's harder to do that. And even as an academic, I have that trouble. There is no line that divides my work and when I come home, I don't stop entirely. And so I always have to find ways to stop myself. And what I've done is I've basically signed myself up for stuff to make me do other things. When my kids were young, I used to go to art class with them. So I signed myself up to do pottery and art. And it was just to force me to not work all the time. And I'm learning how to fly now. I never had the chance or time to do that. So this also forces me to focus my time on something entirely different. I'm a first semester master's student who isn't used to being a planner, but badly needs to become one to make my research program succeed. How do you build a successful plan? How do you make sure you stick to it? So I want to say that my 5-year plan or 10-year plan or whatever I wrote up, I tried to do that with making it all-rounded in mind. So in other words, not only did I have work in there, I also had time for other goals. If I wanted to run a 10-kilometer thing, I would put that down as a goal as well. And it helps me to somehow balance myself to do things that are not just work. And I think it's absolutely necessary to do that, because you cannot be very effective if you're always working. But yes, planning helps to some extent. And all of us are equally I believe that there isn't really anyone who writes a plan and sticks to it. So I think writing the plan is not about writing a plan and sticking to it. It's writing a plan to kind of help guide you to get more done than you would if you hadn't written it. And that's what I say to my students who go out to the Argonne labs as well. I make them plan everything like crazy, hour by hour. And then we get there and the plan just goes out the window. But it's kind of like you can write a plan, and if your plan goes out the window, you know how to organize yourself to salvage as much as you can. But if you didn't write the plan and everything goes out the window, you'll never be able to salvage it as well. So I'd say planning is just writing down what you think you want to achieve, even if it's for the day or for the week, but not going to be so hard on yourself if it doesn't, because it just means that you got more done than you would if you hadn't written that plan. I hope that makes sense, but you don't have to stick to it. The idea behind a plan is not to stick to it entirely. It's about being flexible, but also knowing that you came up with that and you're more likely to achieve 50% of what you plan to do. If you hadn't written it, you might not even have achieved 10. And then understanding that is important. What advice do you have for someone deciding between pursuing a master's or PhD? I think that everybody is different. So it's really about what you want to achieve. A master's is almost something that you should try to do. But if you're trying to decide between a master's and a PhD, think about it like the PhD is long haul. It's a marathon. And to me, the difference between the two is one is shorter. It gives you the credentials you need to be a little bit more specialized than your undergraduate. And it helps you in your work environment. If you are more interested in research-oriented work, in doing, in working in an environment which is research, a research lab or research organization or academia, one of those things, absolutely necessary to do a PhD. Otherwise, if you're working in an industry, it really helps to do the PhD as well, because in the end, I feel like the PhD is part, knowledge gathering in different disciplines, but mostly about being organized and being sort of not being perseverant. So you're kind of like building up perseverance through your research and never giving up, which is an absolute necessity when you're dealing with something that hasn't been solved before, which is what PhD is. PhD is you're dealing with challenging problems that do not have a solution in a textbook or in a paper, but you're going to bring that field forward. You're not going to solve the entire problem, but you're going to contribute part towards it. And that skill in not giving up or persevering is so critical, and it's going to be there by the end of your PhD. You said that you are from Singapore. Did you have your... No, I didn't. In fact, my plan was to finish up my PhD and head back to... Okay, so the question was, you said you were from Singapore. Did you have your citizenship when you were pursuing your job opportunities in the US? And if not, what advice do you have for international students looking for work in the US in aerospace? It's hard. And that is definitely true. I did not have my citizenship. In fact, my plan was to go back home and become a faculty member back home in Singapore. Unfortunately, that didn't materialize. And I did apply for different places here. And it was in my mind that I wanted to become a professor, and I wasn't going to give that up in any way. And so I applied, and of course, in my first couple of years, I still was not a US citizen. I am right now. That didn't help too much for getting certain funding or being part of certain research activities. But the initial stages were there are other opportunities out there, in other words, for funding, which is does not depend on your citizenship. Now, jobs, on the other hand, in industry are a lot harder. So academia is not a place where you have to worry too much if you don't have it. But with industry, jobs are harder if you don't have it. So I think one way is to expand on different fields that you can, get your foot in the door to get something started, and look at various places. In aerospace right now, I know it's hard, but there are a lot of startups, and there are a lot of focus areas, maybe specific to areas which do not require you to necessarily have it, that you should look at and start from there. And then don't tell yourself, like I said, be flexible in terms of what you're offered. Sometimes if you're offered a position that is not exactly what you wanted to do, don't give it up, because you never know what you get out of that. It's kind of like me when I started off and I'm like, maintenance, what am I doing here? But it was really the best place I was. You see, you have to be just open about the opportunities out there, and search widely is what I would say. But yes, I understand it's definitely hard. Did you immediately know what you wanted to do on your thesis on? How did you determine what topic to research? Well, I actually had my mind on multidisciplinary optimization. That was the goal when I came to Purdue. However, I never got the chance to do it. And I know I sat in Dr. Crosley's office and I said, I really want to do the research you're doing. And he didn't have the chance to take me at that time. So I had to go do something else, which I didn't necessarily know about much. And, all I did was I focused on trying to learn as much as I could about the topic I was given. And then I expanded it to what I wanted it to be. So I wanted it to have some component of optimization. So I brought that in somehow. I wanted to do more on the actual application. So I tried to call contacts I tried to call people out at Rolls-Royce and ask them if they would give me samples to do research on coatings. So it started out being very fundamental, basic research on continuing work that was done by a previous student. And then it ended up being more applied like I wanted to. And I started to shape it into what I wanted to. I brought the aspect of the X-ray diffraction and synchrotron studies in on my own because I went to that summer school. So it's almost like you can kind of shape your research to put in all the aspects that you really want. In the end, I did publish a paper with Dr. Crosley from my research, amazingly. So even though I didn't get to be his student, I still managed to publish with him, which is great.
Okay. Do we have any more questions for Professor Raghavan? I guess we're almost out of time here. So I want to thank everyone for coming to our keynote lecture today. Thank you, of course, to Dr. Raghavan for being here. I thought it was fantastic, and I really enjoyed a lot of the advice you gave about masters, and that's where I'm headed next. So I appreciated a lot of that. Thank you all for coming. I'm going to go ahead and end the Zoom call now. Just a reminder that this will be uploaded to our YouTube channel, so you can go back and watch it later. But thank you so much.
All right. Thanks, everyone. I'm so glad to have met all of you.
Thank you, Professor.